Good afternoon, everyone. I'm here to give a quick review on ion guns, particularly our gas cluster ion source. I'll also be mentioning just general sputter sources as well, amongst matters. I've given similar talks in previous user meetings, so you may well have heard lots before. So I've tried to include some slightly different material in this time as well. So on we go. So just a quick outline. I'm just going to give you a brief introduction about why we use argon cluster ions, or any other ions for that matter, what use they are for surface analysis. Then give you a quick overview of the Kratos gas cluster ion source, the GCIS, and then just talk about three key parameters we're looking for when we're considering how to use the gas cluster ion source or any other ion gun. So firstly, sputtering yield, secondly, chemical integrity, and thirdly, the characteristics of our crater and depth profile resolution. So firstly, why argon cluster ions? So we've got three types of material up there that the analysts may be interested in. So elemental metals firstly. So traditionally everyone's just used noble gas ions to sputter these elements, so either to clean, remove contaminants from the surface, or to profile down, collecting XPS spectra as you go, and tunnel down the sample, and that's proved very effective for decades. But unfortunately, when you move to say inorganics, with a mixture of elements in, you can, although you do it at a reasonable speed in terms of the experimental time frame, you can often suffer from and preferential sputtering of the species. So light species such as oxygen may be removed preferentially in comparison to heavy species such as metal atoms. So that can give you a distorted picture of the chemistry that's going on in your sample. Then thirdly, if we try noble ions, particularly argon, with polymers or organics, then we'll quickly run into trouble. We'll get very inaccurate results, very slow and very tedious. Sometimes you can call upon a bag of tricks to try and get you around that fundamental limitation, such as cooling the sample using grazing angles of incidence, but often it can be quite time consuming to get any meaningful data out. So along came various polyatomic sources, such as we still sell our coronium ion source. So that helps to mitigate the problem by spreading the energy in your projectile over several different atomic centers. So along came what's now the kind of standard in surface analysis, using argon cluster ions. So these are big balls of argon. So the argon's held together by van der Waals forces. So they're weakly held together like giant ice balls floating through your vacuum system. So these have proved very popular and effective. So if we move to our simple categories of material, for sputtering metals and elemental targets, it's very accurate. It does suffer from, it isn't as fast as using noble ions. Inorganics, again, you can remove this, the negative effects of preferential sputtering, so you get a more accurate picture, although often it can be at the expense of speed, although not always. But polymers organics is where it really does shine, and that's really, really important for a lot of new materials, where it gives excellent accuracy at really good speeds. So it makes sputtering analysis, particularly 3D analysis of a whole host of materials, now readily available to the surface analyst. So what's in an ion source? So if we take our noble ion source, what we have basically gas in. So we just bleed gas in. In our case, it's usually argon, although you can use, say, neon or whatever other kind of ions may be taking your fancy. So we just bleed them into what we call the EI source region, so electron impact source. So this is up here. So this is similar to what you find in a residual gas analyzer or the basic mass spectrometer. So the gas flows into this open volume, which is enclosed in a transparent grid. The grid is held at our beam energy. So if we're supplying argon atoms of 5 kV, so argon ions of 5 kV, we hold that at 5,000 volts. Adjacent to this grid, we have a filament, typically tungsten. We basically pass the current through the filament. It produces electrons. The electrons are then accelerated through the grid, where they ionize our argon gas, and typically about 140 eV ionization energy. And then we have at the opening to this grid, we have a negatively biased electrode called the extractor, and then that pulls the argon ions out into our lens column. So our lens column typically consists of 2 elements: the condenser lens and a focus lens, and that helps give you a small amount of demagnification on your target. So it can give you, depending on the instrument and your configuration, so you might end up with an argon ion target from like 100 microns to even up to a millimeter in the XPS world. Though in the Sims world, it might be much smaller. In other worlds, it can get up to the size of centimeters. So that's the basic architecture that you'll find in most ion guns commercially available. For an argon cluster ion source, it's more or less the similar idea, but instead of bleeding in just argon gas, we have to supply a stream of clusters that enter coaxially from the top of the ion column. So that's really where the tricky bit comes in. So this next couple of slides are just going to illustrate that for us. So how do we get our little fragments of argon into an electron impact source, which you have to hold a kind of medium vacuum? So we start off with an argon cylinder, and we charge that argon cylinder and the outlet line to a few bar pressure, what we call the stagnation pressure. And at the exit to that outlet line, we have a nozzle. So this is just it's basically a very small orifice with a shaped exit cone. So that is to use Bernoulli's principle. So we're converting the internal energy of the gas into forward direction, into forward momentum. So the idea being the internal energy of the gas drops, so everything freezes. So that's illustrated by this picture available from Wikipedia of how, in this case, water in the air is condensing, is freezing as a result of being imparted this backwards momentum in this case. Okay, so this is just illustrating the principle of how we form our supersonic adiabatic expansion. So in principle, it can be any orifice, which is suitably sized, where the aperture is a lot larger than the mean free. Sorry, that's the wrong way around. That so where the aperture size is a lot smaller than the mean free path. And when the gas expands out from the high pressure region P0 into a vacuum here, then it will form this supersonic adiabatic expansion with forward directed momentum. And if we take a look at these graphs here, these show the velocity distributions within the graph as a function of the pressure and as we move along that expansion. So we start off in the high pressure vessel here behind the nozzle orifice. We have a Maxwell-Boltzmann type distribution with everything kind of randomly orientated. And as we move out here at the nozzle orifice, our gas stream will reach sonic velocity. And as it expands further, it will reach supersonic velocity as the Mach number continues to grow. As the Mach number continues to grow, the peak in this velocity distribution increases, but importantly, the spread in the velocity distribution collapses, so eventually it's really small. So this means that all our internal energy is now in kinetic energy, and all of the adjacent argon atoms, they're not striking each other. So in other words, they're frozen out. And so at some point within here, you'll get argon atoms colliding with each other and they'll stick and they won't fall apart because the internal temperature is just too small. So this requires to handle such a high gas load through a nozzle, it requires differential pumping to be placed on top of our ion gun. So that's why we have to have, and the gas cluster ion source, they look a lot bulkier than a normal, just a normal, say, mini beam 4, for instance. So we have to have 2 differential pump stages. So after our gas escapes through the nozzle, it's initially at P0, you get down to pressure P1 here, which is in usually the millitorr region. That's pumped by its own individual turbo pump. And then clusters are sampled by a molecular beam skimmer, which is just a very thin cone, which is the aim of which is to not reflect back any clusters. Then behind there sits another stage of differential pumping held at something like 10 to minus 4, 10 to minus 5 torr. And then behind that, another aperture. In there, we reach our EI source there. So this pressure here would typically be into the 10 to minus 6 torr region. So our particular embodiment of the gas cluster ion source is what you see here, the Kratos GCIS. So it's just a quick schematic. So here we have our cluster generator at the back, so nozzle, skimmer, aperture, and then here we have our EI source. And we have the same principle of optics here. So we're using a negative potential to extract the positive ions formed within the EI source forwards through an electrostatic lens column. But what's different to a conventional ion source here is we have a Wien filter in the central portion of our ion column. So this is basically a crossed electrostatic and magnetic field. So the idea being that the magnetic field steers all of the very light ions, argon, monomers, dimers, trimers, out of the column, so they don't go on, travel forward, and then potentially damage your sample. It also allows you a degree of mass selection. So that following the Wien filter, they're passed down through an electrostatic bend to filter out all metastable atoms, and then finally focused and demagnified onto the sample as for a noble ion gas source. So just a quick note on the Wien filter. So coming out of our nozzle, we'll have a distribution of cluster sizes. So that's schematically represented by this red distribution here. So the Wien filter allows us to select a portion of this very roughly. It's not a very precise mass filter, but it gives you some control over the size distribution that lands on your target. In addition to this, we also use different ion EI source conditions to kind of optimize the cluster size of the ions that you see at the end of your ion gun. So move on to sputtering here. So one of our first considerations. So if we're looking at sputtering samples with noble ions, such as Argon Plus, typically, the sputter yields are been described by Sigmund's law or variations thereof. And so I've presented it here in its most crude and simple form. So it just states here that the yield is proportional to the beam energy, that's E, divided by U. So U is the surface binding energy, but in elemental solids, it can often be equated with the enthalpy of sublimation. And so I've included just a table, a few values of U here for some elements, along with an example plot of data derived using Sigmund's law here. So you can see that as the kinetic energy goes up, the sputtering yield goes up, but eventually that increase tails off as it scales with the square root of the kinetic energy. In addition, an element like platinum with a higher surface binding energy is more difficult to sputter than something like silver. The characteristic mechanism with noble ion sputtering is that when they impinge upon the target, they'll induce this deep solid penetration and a collision cascade which points downwards into the sample. So you can see that not much. This is a snippet from a molecular dynamics simulation. You can see not much material is ejected from the surface. Rather, there's lots of downward mixing occurring, and it goes really to can burrow down to quite a deep distance, certainly deeper than the XPS information distance. Sputtering yields, on the other hand, for clusters are described by more complex relationships. These relationships were nicely described by Martin Sear and Steve Spencer at MPL. In this case, we're not looking at just the direct energy surface binding energy relationship. The key parameters are really the energy divided by the size of the cluster. So E divided by N, so the energy per nucleon in our cluster. In this formula here, which is kind of the master formula to describe the sputtering yields, the A parameter in this case is material specific, so it relates to the surface binding energy of the target. Usually A for elemental targets and inorganics is pretty high, about 50 EV, whereas for polymers and organics it can be very low, about 3 to 4 EV. The important difference from clusters to just normal noble ion sputtering is that instead of this downwards collision cascade, you have this crater-like impact. So kind of shock wave is resident at the surface of our target, and that creates that kind of a heating effect and a lot of lateral sputtering, and a lot of material is then ejected upwards instead of downwards. So here's some example produced by a group of Martin Sear. So there's a couple of examples here. So these are the curves for polystyrene at the bottom and silicon dioxide at the top. All of the curves show this kind of structure where you have a kind of linear increase followed by a knee before you get into a shallower gradient in the high energy over cluster size regime. The key point to take home from these two is that the silicon dioxide curve is kind of shifted down by an order of magnitude in terms of yield compared to the polystyrene, and that reflects the higher surface binding energy of those types of material. So what does all that mean for the practical surface analyst? So I've included here some very, very rough ballpark figures. So all of you will probably have an argon source. So I've included argon at 5 kV and 500 EV, and I've matched that with kind of typical fluences that you'll get, say, on a Kratos or one of our competitors' instruments. So this is reflections, not just the total ion beam current, but it also reflects on the probe size as well. So if we go to our Sigmund's law type calculations, we get yields in terms of nanometers cubed per ion, like below unity. So it's really quite low per ion. And then if you want to work out the etch rate, so that's obviously a product of the fluence and the yield, and we can get up to about, say, 10 nanometers per minute plus for metals in organics using a noble ion source. Whereas if you want to go more slowly, maybe do more high resolution depth profiling with a 500 EV source, that etch rate might drop by a couple of orders of magnitude. So that's the result of not only the lower yield, but the lower achievable ion beam intensity and the larger spot size. Because the lower you go in terms of ion energy, the harder it is to focus. So therefore, the spots tend to get larger. And I've left these boxes here for organics as blank because usually there's a lot of work to get any kind of meaningful data out of those. And now I've gone on to include some typical clusters. So I've included 5 kV clusters and 20 kV clusters at sizes of 500 and 2000. So you can see here the first thing that jumps out is the fluences achievable are much, much less than with a noble ion source. That's because we're kind of limited by that supersonic expansion at the top of our ion guns and the amount of material we can actually bring through it and keep it all on a kind of experimentally realizable vacuum rig. But nonetheless, if you look to the neighboring yield, both for metals and organics, the yields are much higher in terms of the amount of material ejected per cluster ion impact. And that's because you've got this really pronounced strong heating effect at the surface, which results in this explosion of target material across the sample and upwards. Nothing goes down. So it's very efficient per cluster ion. That's the key. So you put those two together again. And for metals and organics, you can approach the same kind of etch rates as you do with a traditional noble ion source, providing you operate towards the smaller cluster sizes at higher beam energies. If you're doing it at, say, 10 kV, 5 kV, then it is still going to be really quite slow. Whereas if you move on to the organics, you can see the yields are phenomenal, and you can really cut through stuff really quite quickly. So I'm going to just illustrate that with a couple of examples. So here's one example. We have a multi-layer stack of alternating polymers, AB, AB, AB. A is a polyester, B is a methacrylate, and you can distinguish them easily in the XPS. I won't go much into that. So we can successfully bore down that whole 1 micron layer, and we can easily elucidate the interface between polymers A and B, even down to 1 micron. And this is actually old vision data, as you can see here, but this is taking on the order of 2,000 seconds to get through. So that's quite easily experimentally realizable and convenient. Now, if we switch it up a bit and we substitute one of our polymers in that stack for a sort of silicon dioxide, things look a lot different. So instead of these evenly shaped layers, we see in our depth profile, it takes much longer. And so the polymers now are compressed into this tiny little experimental time frame here by these sharp peaks. Whereas it's taking us about 4,000 seconds to get through each one of those inorganic layers. So it's just a good example to show the considerations you need when depth profiling different types of target material. So then chemical integrity. So the key when sputtering anything, even for cleaning or depth profiling, is we want to maintain that chemical integrity. So we want a faithful representation in our spectra of what it was before we touched it. So sometimes the key to that, so we've got this inequality on the board. So the key is that the damage you induce with your ion, so you're always going to induce some kind of damage, no matter how small, is always a lot less than your sputter yield. So you can, in principle, damage everything, but as long as you're then removing that damaged material, that's absolutely fine. So sometimes it's hard to know which side of this inequality we have to work on. So sometimes we have to minimize our damage, and sometimes we have to maximize our sputter yield to get the best results. So just a couple of quick examples. So this is polyimide. So this is a type 1 polymer. So when you bombard a type 1 polymer with ions, it degrades by cross-linking. So it wants to, once you smash it up, it wants to then go and mate with other bits of polymer around, which isn't ideal because you want it to be ejected into the vacuum. So this is a tough nut to crack. And so we have C1s spectra and N1s spectra after zapping it with ions for cluster ions for a certain same fluence. And we can see, so we've got the red spectra is after 20 kV argon 500. So this is way into that high EN regime, compared to the blue curve, which is data from our 10 kV argon 1000. So the C1s spectra after zapping our polymer with the 20 kV, you can see this kind of peak up here. So this sharp peak about 284. So that's our typical graphite peak. So that's everything's turning. There's a little bit of mush in there. And similarly in the nitrogen 1s. So the higher binding energy peak is the kind of pristine polyimide peak. There's a lower binding energy peak here, which results from damage. And you can see that's quite prevalent. That's quite strong from the 20 kV data. Whereas you compare it to the 10 kV data, you can see this graphite peak is not really there at all. These satellite peaks appear much more intensely. And you can tell from that separation there that things look pretty good. And otherwise, when we look at the N1S peak, you can see there's a very small damage component, but it's not very big at all. So that's the case of where we've had to work to minimize our damage by decreasing the energy and increasing the cluster size. Now we have another example where the opposite is true. So this is some data that we obtained using samples donated to us by James McGettrick at Swansea University. And so he's interested in these interesting perovskite solar active type materials. And so we were interested naturally in depth profiling them with the cluster beam. And so we did just that. The key point to mark out here is we're looking at this lead 0 intensity here. What we suspected was when you bombarded this material with any ions, what you do is you reduce the lead components quite quickly. So you just end up with an awful lot of metallic lead. So this is our 10 kV Argon 1000, and you can see our lead 0 component goes from about 30% to about 45%, going from 0 at a time to say 1,000 seconds at a time. So the question is that real or not? We weren't really sure. So then we tried, and it's 20 kV Argon 500. So in this case, we're increasing the energy, decreasing the cluster size. And you can see in this case that the lead 0 component is much less pronounced. This increase is about half seen at this one. So this is kind of suggestive of a regime where we're trying to maximize the sputter yield in order to maintain a more faithful representation of our chemistry. Unfortunately, I don't have a golden rule about which side you have to maximize or minimize for what kind of material. I think most analysts would have to put some time and effort into to work out which is right for their particular systems. Although I would say that sometimes it happens more often with inorganic materials that you have to maximize the sputter yield, whereas organic polymers are generally safer with trying to minimize the damage. Okay, then to move on to crater characteristics. So we've also got to consider this when using ion sources. So in an ideal world, we had this kind of multi-layer sample like this. All our craters were always like this. They'll just have like infinitely steep sides and really flat bottoms. So when we're acquiring XPS spectra, it would just be determined by XPS information depth and any kind of interatomic mixing as a result of ion bombardment. And in this case, you can sample from anywhere within the crater, and it should make a difference. But in reality, our craters don't quite look like this. So this is, every real crater will have a curved edge like this on the bottom, and that will be defined by the size of the ion beam full width at maximum, so your probe size. And so for XPS instruments, those probe sizes are typically in the region of about 300 to maybe 500 microns. And this is some example data of what one of our actual craters look like. This was donated to us from EPFL. So you can see on the top right-hand corner this is a top-down photograph after etching. They had some kind of multi-layer sample. So you can see this grey here is the bottom of the crater, and you can see these bits around the side of the edges of the crater. So they obviously set their ion beam to raster across that whole image, but the actual realizable bottom of the crater is obviously smaller than that image. And below that, they've recorded some AFM data of this crater bottom here. So you can quite clearly see we've got these steep sides. So across, this is 1 millimeter in total across. It's actually quite a small crater they've gone for here. Normally we'd go for 1.5 mils kind of minimum. But you can see, even though it's quite a small crater, there's still a significant portion, about half of it, is relatively flat at the bottom. That's good. You do also notice with gas cluster ion sources that the sides tend to be a bit asymmetrical. So you'll have one steep side and the other side, an opposing side, might not be so steep. But fortunately, I've seen that with other competitors, so I'm not worried. Okay, so then the other factor you've got to bear in mind is the topology, the microstructure induced by your ion beams. So when you sputter any sample with just Argon Plus, typically like 45 degrees, 50 degrees, which is what we do in our instruments. We don't typically use normal incidence sputtering. You'll see kind of these craggy hill formations if you look at it under an AFM, and the RMS kind of roughness can get up to about 10 nanometers. But I think from what I've seen in the literature, it tends to kind of get up to 10 nanometers, but doesn't go much further than that. And that kind of sputtered topography will be the limit in an ideal depth profiling experiment for your resolution. Whereas with cluster sputtering, what you'll get is ripple formation. Interestingly, you do see ripple formation with noble ion sputtering, but only at higher energies or really, really low energies. And these ripples are quite pronounced, and the RMS kind of roughness does tend to scale, I believe, with depth. Although I've not seen any data for going really, really low, how rough it can get. So this is just an AFM from the literature. So it shows these quite kind of nice ripples, kind of structure you might find on a beach just below the shoreline. So again, that's going to limit your resolution. So now your crater is going to look in reality something like this. And so this is going to jumble up your XPS data. So it's something you've always got to be aware of. So just to sum up, here are my tips. Firstly, consider the chemistry of what you're doing. If you've got an elemental solid, you might as well just use 4 or 5 kV Argon Plus, because it's usually a bit faster than a cluster beam. But otherwise, if you've got any kind of inorganic or organic polymer, always consider going for the cluster. 10 kV Argon 1000 is our workhorse kind of cluster setting, so it's always good for a first go. Then kind of choose your cluster beams that you've got to balance different factors, your etch rate, chemical integrity, and then the depth profile resolution. So depth profile resolution will scale with how much topography and how flat our crater is. Okay, rule of thumb, go for an ion gun crater size of like 10 times your XPS analysis area. So if you're using, say, on our instrument, say 110 micron aperture, go for a minimum crater size of like 1.2 millimeters by 1.2 millimeters. So that's to make sure you're always sampling in the middle and the flat bit of the crater. And then the fourth one, if you want really good resolution, you have to employ sample rotation. That's really important if you're going to very large depths as well, because that surface topography will just keep building and building and building. If you're just doing a shallow clean of something, then it really doesn't matter. If you want really accurate results, then I'd recommend the rotation. Okay, thanks very much.